Hi everyone, and welcome to the next session. It's a pleasure to have with us Amit Kumar from IIT Delhi. Amit has done fantastic work in several areas of computer science, including approximation algorithms, online algorithms, and data structures. He also has the dubious. He also has the dubious distinction of being my PhD advisor. I can attest that while his ideas may be very hard to understand how he got them, but he's definitely an experienced speaker. So I'm looking forward to a nice talk on online convex paging. So take it away.
Thank you, Jatin, and thank you, organizers, for inviting me here. It's a pleasure being here. Today, I'll talk about an online problem. I know many of you may not be familiar with this. So this is joint work with Anupam Gupta at NYU and Debmalya Panigrahi at Duke. So as the title suggests, it's online convex paging. So online paging is a very well-studied problem in online algorithms. I'll say what it is. The word convex sort of just makes it more general. And so as we go along, I'll define it. So this is the outline. So I'll just give you a very brief outline of what online algorithms are, just in case you're not familiar. Then I'll just go over some classical results and some techniques maybe. Then I'll talk about slightly more general version of online paging. It's called weighted paging, where pages have weights, and so you'll see why it is relevant. Then I'll define a special version of this convex paging problem called min-max paging, which again has been studied over the years. And the algorithm here that we have is quite simple. And in fact, I plan to present the entire analysis today. So as you will see, the ideas are fairly simple. So I'll just mention the lower bounds, but I hope to give you the complete analysis for the algorithm. And then, I'll just talk a little bit about what is, how do you generalize, extend it to the more difficult case of convex paging. Okay, so that's the plan. So let's begin with online algorithm. So typically in an offline algorithm, the way it works is that we are given the input and you are supposed to design an algorithm with sort of required sort of specifications. But in the online setting, the input is not given upfront, but it arrives over time. Okay, so this is some algorithm, and this input keeps arriving. So initially there's some input, then it produces a solution, and then some more input arrives, and then the algorithm changes its solution. Right, so the solution adapts or changes as the input keeps coming. Okay, so the point is, if the algorithm knew the entire input in advance, it could have done something better. But because it does not know what the input is, it tries to sort of build a solution, which hopefully would be good. Okay, so let me just directly come to the exact online paging problem. So of course, you can formulate many problems in that setting, but this is the one that we are going to discuss. So again, the problem is very simple. It says that you have a set of n distinct pages. So think of these as n colors. But I have a cache, I have some sort of a bag which can only hold a much smaller number of pages. So it can only hold k pages. So think of k as some number which is much smaller than n. So I have a cache which can only store, let's say, 2 pages here. So k is 2 in this case. And what happens is that at each time, so the input is essentially giving you identity of a page. So at each time you receive a page request. Okay, so at each time t, a request for a page arrives. So if you're thinking of pages as colors, so at each time one new color arrives. And what you want to do is you want to make sure that this color here is in your cache. Okay. So for example, if this is the first input, then it's already in your cache. Good, nothing happens. And the next time some other page request arrives, which is not in your cache, so we need to throw away one of these 2 colors and bring this one inside. Okay. So maybe you throw away that one and this guy comes in. Next time some other request arrives, and then you again have to do the same thing. Okay. So and so on and so forth. Okay. And what is my goal? My goal is to minimize the number of cache evictions. Cache eviction basically says that if you look at a particular page, you can count how many times it was evicted from the cache. And so you sum this over all the pages. That is what you want to minimize. Okay. So it's a very classical problem, and we teach normally in algorithms that if I were given the entire input, if you knew the entire sequence in advance, then there is very natural greedy algorithm for this, which says that look at you have, suppose the page that you're seeing is not in your cache, then you look in the future and see which one is the most is requested for this in the future. That's the one you throw away. But of course, here we don't know the future, so people design various kind of heuristics. There's also very widely studies, as you can imagine, in operating systems, architecture, and other settings, because it's a very fundamental problem. Okay, now, okay, so suppose I have some algorithm for this. How do I understand, what is the, how do I sort of make sense of the performance of the algorithm? So we define something called a competitive ratio. It says that, fix a request sequence, right? And see how much cost this online algorithm incurs, how many evictions it does, and divide that by, by the offline algorithm, by the optimal offline algorithm. So suppose somebody knew the entire future, how many evictions it would have done, take that ratio. So of course, this will be less than 1, but the closer it is to 1, then the better the algorithm is, right? Sorry, it's always bigger than 1, but the closer it is to 1, the better the algorithm. Okay, and normally, when we take the supremum over all possible requests, we always think of the request sequence as very long. So you do some sort of, you look at it in some sort of asymptotic sense, because you assume that all of these numbers are very large. Okay, so let's quickly summarize what is known about this problem. So again, as I said, if you knew the entire input, then for this in future is known to be optimal. It's also very easy to show that you cannot get better than k, where k, remember, is the size of that cache, competitive ratio. In the sense, what does this say? It says that there are inputs for which the algorithm will perform at least as bad as k times the best possible offline input. So if somebody knew the entire input, it can beat you by a factor k. That's pretty pessimistic, right? So let me just show you why that is true, and it's very simple. So for example, suppose some adversary is trying to fool the algorithm and knows what your cache looks like. So at each time, the adversary will give you a page which is not in the cache, right? So suppose there are cache sizes k, the number of pages is exactly 1 more than k, so k plus 1. But at each time, it will send you a request which is not in your cache. So you will keep incurring cache miss at every time, whereas somebody who knew the future would only incur it once in every k steps. So you can easily show that competitive ratio is at least k, right? I mean, so this is the, somebody can easily design an algorithm to fool, design an input to fool any algorithm. So people also know algorithms which are k competitive, so you can actually achieve this bound. So for example, LRU, and there are many other algorithms also. So basically, you can see why it is k competitive. LRU says that instead of looking at the future, you look at the past. Okay, so I don't have to, I mean, we don't have to worry about this. But now the question is, if we allow randomization, can we beat this bound of k here? So you should ask, like, what does that statement even means? So suppose my online algorithm is randomized, how can I get around this factor k? And the idea is that the adversary who is designing these inputs for the algorithm doesn't get to see the coin tosses of this algorithm. So that's why randomization may help the algorithm, because now the adversary cannot predict what is the worst possible sequence for the algorithm. It cannot design a sequence like this. So, all right. So just to fix the notation. So what does it mean for competitive ratio? So if the algorithm is randomized, then I'll just define expected competitive ratio as the ratio of these two things: the expected cost of the algorithm by the cost of the offline optimum. That doesn't have to be randomized because it knows the input. Okay. You can also see that there's nothing about efficiency here, right? We are not saying that the algorithm has to be efficient, but most of the time you would want algorithms which are efficient. Okay, and there are now versions of LRU which are called randomized LRU. I will not get into those, which actually give you log k. So they improve that k to log k. Okay. So just to give you a sense of why randomization helps, let me give you a toy example, and you will see that this is a special setting of paging, and it will also sort of convince you why would randomization help. Okay. So imagine the following problem. Okay. So I'll call it airline seat problem, and this is actually a special case of paging. So let's say there are n seats in a plane, okay, and you forgot your seat number, okay. So you can sit anywhere in this. You are the first person to enter the plane, so you sit somewhere, and now people are going to arrive, okay. And if you're sitting on a person's seat, then when the person shows up, you will have to get up and go somewhere else, okay. So now the question is, how many times do I have to change my seats, okay? Right, so flight with n seats, you forget your seat number. Now, why is this like caching? This is caching, like caching, because you can imagine a cache of size n minus 1. And the place where you are sitting, that's the page which is not there in the cache, right? So when a person comes, it's like saying that page request has come. So you have to bring that person in. So you have to go and sit somewhere else, right? Some other page goes away. So it's exactly like caching. It's a special case, but you can show that this is essentially the hardness of the problem. Okay? So, okay, so, right. So what do you think? How many times do I have to switch seats in the worst case? N times, right? I mean, because what if the sequence of the arriving people are such that each time, wherever I'm sitting, the next person just comes there. This is assuming that somebody knows your strategy, right? There's an adversary who knows what you're going to do and designs this input. But suppose now I use a randomized strategy, right? I say that each time I have to get up, I go to a randomly chosen seat. Now, what is the expected number of seat switches I have to make? And you can see this would be like log n, right? Why? Because when I'm sitting at a particular seat and I chose a random seat, the chance that about half the people will go by before somebody shows up on your seat, right? So about n by 2 people will go by before somebody comes at your seat, and n by 2 seats are remaining. Then again you go to some randomly chosen seat. Again, roughly half the people have to show up before somebody shows up at your seat. So so essentially it is a log n, right? And essentially that's the idea also why some a randomized version of LRU will give you a log k approximation, right? Essentially that's the idea. There's a slightly different way of looking at it. Slightly different way is that suppose I was allowed to sit on fractionally sit on the seats. That is, I was allowed to sort of occupy fractions of seats, right? 1/3 of the seat, 1/4 of the seat, and so on, so that all the fractions add up to 1. Okay. So then what will I do? Well, I'll say that because I have no idea how people are going to arrive, let me pick 1 by n of each of these seats. And when somebody shows up on a particular seat, I have to vacate that seat completely. So my 1 by n fraction of that seat goes away, and then I smear over 1 by n minus 1 over all the remaining ones, and I keep doing it. And so at each step, you are essentially, at the ith step, you're changing your distribution by only 1 over I, because you're throwing away 1 by I fraction on that particular seat which is getting occupied. So again, the total movement cost would be like 1 by n plus 1 by n minus 1 all the way to 1, which is actually like log. So this is, so we'll come to fractional algorithms. So this is, kind of motivating that, right? I mean, if you were to fractionally occupy things, then you don't incur what you would incur if you were to just sit on one of the seats. Okay. So randomized LRU, it's known to be log k competitive. Essentially, that's the idea. But of course, one has to extend that proof. One can also show that essentially that example also gives you a lower bound. So anything has to be at least log k competitive. Can't do better than that. Okay, so that's essentially says that almost everything about this problem. Let me just come back to the next one. It's called weighted paging. So what is weighted paging? Weighted paging is again like online paging, but every page has a weight. Okay, so why is this useful? Because you can imagine that different pages could be of different sizes, and evicting each of them, maybe some of them are sitting far away. So evicting each of them could cost a different amount of time or something. So that's why people look at this weighted version where every page has a different weight, and you want to minimize the weighted eviction cost. So when you throw away a particular page, you incur WI cost. Okay. Again, similar algorithms are known. So for example, Krobach, Karloff, Payne, and Vishwanathan, I think this was in the 90s, they showed that one can get, again, a deterministic order k competitive algorithm, right? So the same, almost up to some constant, you can get the same competitive ratio. getting log k competitive for this problem, even though it looks very simple, was open for a long time. And only around 2007, Bansal Bukbinder Naur came up with an algorithm for this. I will not go over this, but this was a new idea here. So I'll tell you what that idea was. This algorithm was inspired by thinking of a weighted paging problem as a set cover problem. So I'll show you how it can be thought of as a set cover problem. So so let me just talk, maybe spend 2 slides. We won't need this precisely. So even if you have not seen fractional sort of linear programs or something like that, it's not necessary, but just want to give you insights on how those algorithms work. So again, as I said, in the airline seat problem, the idea is to use think of the fractional version of these problems. The reason why fractional versions help is because then you can make this problem, in a continuous, think of it as a continuous problem. So you can apply various methods in continuous optimization. Okay. So what does fraction mean? That unlike saying that every page is present to an extent of 1, the cache can hold fractions of a page. So this cache is, for example, holding half of this page, and full of this page. Okay, so whatever that means, right? It's only sort of a conceptual thing. It won't happen in practice. And so if I denote ypt as a variable which says that what fraction of a page is in the cache at a particular time, then the only constraints I have is that if pt is the page that you're requesting, then that has to be there in the cache. So that has to be there to an extent of 1. Other guys can be present to some fractions. Okay, and again, what are the constraints? The constraints are that if you add up all the pages, then their total fractions cannot be more than k. And at each time, I'm going to change this solution. So at this time, for example, I have 1 of this, half of this, half of this. Later on, I'll have some other fractions. So how do I measure how much my fractional cost has changed? My cost has changed. Well, for every page p, you are going from this much fraction to this much fraction. So that difference is how much you pay, right? And if you're looking at weighted paging, then you'll just multiply this by the weight of the page, right? So essentially, everything extends in a very natural manner, right? So you look at the L1 difference between the 2 vectors. Okay. So so far so good. Questions? T is the time. So yeah. Over, yes, you're spreading it over all time, right? Summing it over all time. Okay. It's more useful to think of the negation of this variable, which is saying that how much of the fraction of the page is not in the cache. And the reason is because if you look at this constraint, it looks like a packing constraint. And it's more useful to work with covering constraints. So then it begins to look like set cover. So if you look at the opposite of it, then it says that for the page which is requested at time t, this guy should not be there in the cache. So should be there in the cache. So x which is the fraction which is not in the cache, should be 0, right? So you just sort of mentally switch everything. So the constraints which were saying that something should be less than equal to k, if you take negation of everything, then it becomes like the negation of all of those should be at least n minus k. So, so there's nothing much happening here, but this becomes like a set cover constraint, or not a set cover, but a covering constraint. And then you can apply techniques from online set cover, and those things were known already to sort of solve for this. Okay, so there were online algorithms. So what does it mean to say that online algorithm for these variables? So they will maintain these variables in an online sense. And for any page p, this xpt will evolve in a certain way. Okay, so anyway, so that was so the reason why I'm bringing it up is that all of these algorithms had a 2-step process. The way it was that initially at each time t, some page is requested, the algorithm maintains a fractional solution xt, right? It says that how much fraction of a page is present on the cache. And on the side, it is also supposed to present to the actual sort of user an integral solution, right? Whoever is using this algorithm cannot use these fractions. So actually on the side, it has to produce an actually integral solution. It has to say which pages are present in the cache, which are not present in the cache, right? This is only for sort of conceptual reasons. Then again, some other input arrives. and this fractional solution changes to something else, then again it sort of changes this integral solution. So this is what you get to see as an output, but this is being used by the algorithm, and so on and so forth. Okay. This part turns out to be deterministic. Okay. So the known algorithms here, and you can see why, because if you use randomized, is like taking an expectation over these fractions, which is again fractions. So you would not have one would not expect this step to be randomized, because anyway I'm producing a fractional solution, and this step uses randomization. Okay, so going from fractional to integral, this requires some sort of rounding here. Okay, so what they showed, Bansal, Bukbinder, now that you can, when you do this if you maintain a fractional solution, I only incur a log k loss in the comparative ratio. Okay, whereas in the rounding you only lose a constant loss, and so this overall it becomes a log k comparative algorithm. So that's the high level picture. Okay, I mean this is all you need to know. Okay. Okay, so and this is a very commonly used template. So people have used this template for many other algorithms. K-server and many other sort of open problems in this area got resolved using this template. Okay, so now let me talk about the actual kind of problems I'm going to discuss. So now there's one notation I'm going to fix. So let's say you have some paging problem, and for each page I, let yi denote the total number of evictions this page I incurs over the entire period of the input. Okay, and so the paging problem says that you want to minimize the sum over all pages of how many times this page is evicted, right? And weighted paging just says wi. Min-max paging says that you minimize the L infinity norm of this vector, which is that minimize the maximum. So it's saying that minimize the maximum number of times a page is evicted. So you can imagine some sort of fairness constraint where you don't want any user or any page to be evicted too many times. So this is what it is addressing. Okay. So no page should be evicted too many times. And then you can imagine other versions. You can imagine LP norm. You can say that let me take the LP norm of this vector. Right? So you're looking at a vector of all the yi's. So this is one extreme and this is the other extreme. So how about an LP norm? And in general, you can ask, how about a convex function, right? Any function. So if you give me the vector y1 up to yn, so g of y1 up to yn is any function, any monotone function on the yi's, and I want to minimize g of y1 to yn. Okay. So for example, let me just give some specific settings where this would be useful. So for example, let's say the pages are coming. I'm dividing the pages into groups. Each page is belonging to some application. So I'm running 3 different applications, and each page belongs to one of the applications. And if you look at the cost incurred by each application, it is the total paging cost, right? You add up the total cache misses of all the pages in each of those applications. But then you want to take the max over all those. So you can imagine that I have some complicated function here which groups these pages and defines an objective function for each of those groups and then combines them and so on. So all of those would be captured by such functions. Okay, so this is a fairly general class of functions, which is which captures more than what is here. This has been studied in many settings actually. Such functions, people give different names to this, but essentially the properties are that it should be convex, differentiable, monotone in each of the yi's, which also makes sense. If I increase the number of evictions of a page, this g should go up. This is less intuitive. It says that the gradient of g is also monotone, so it is some sort of super modularity, right? So it says that if you look at the gradient of g, even those, if I increase any of the yi's, they should go up. It should grow. So I mean, the mapping between these two is that you ignore this 1 by p factor. So if you think of g as summation over I yi to the p, that would be another example of this g, right? And this is saying that so this is saying that how far away it is from being a linear function. So it says that this is a technical condition. It says that if you look at the gradient of g and take its dot product with y, Okay, so imagine that this was a linear function, right? G of y was y. Then this would be just y, okay, and this would also be just y. So it's just saying that how far away it is from being linear. So suppose g of y was y to the power p. So this would be y to the p plus 1. Sorry, p times y to the p, and this would be just y to the p. So you will get this factor p here. So if g of y is like y to the p, then this p and this p exactly match. Okay. Otherwise, it's just saying that how far away, in some sense, measuring how far away this g is from being linear. So p is a parameter, and various names are there. So I'm just calling it p bounded convexity, but people use other names also. Okay. So I won't get into this, but I'm just showing you that there are all these definitions.
So this grad G is monotone condition. So isn't that implied by convexity? It's coordinate wise monotone?
No. Any. So this is not symmetric. This is not symmetric. This is page 1, page 2 up to page n, right?
Yes, but like, so if I take the gradient along, say, the y, the worst.
The gradient. So you look at the gradient of G,
yes,
and if I increase any of the coordinates, it is also monotone in that.
The vector, right?
It's a vector.
And so each coordinate.
Each coordinate, yeah. So when I say
each coordinate is a monotone as a function of each other coordinate. Okay, that's strong.
Thanks. Yeah. So when I say so even here, if I vary, just fix everything and just vary one coordinate. Okay, so let me know what is known about these problems. And there are a lot of results. I mean, I'll say a few things, but I hope that the algorithm that you will see eventually will be very simple. So okay, so for upper bounds, remember for paging we had order k, so you incur an extra log factor here. Okay? So log n. If you had just weighted paging or paging, this log n would not have been there. But now, if you're looking at the L infinity norm, you incur an extra log n factor. Okay, so this was known by Minash and Singh in 15. Lower bounds. So the thing in red is our contribution. So before that, almost a tight lower bound was also known. So this is almost matching. So Chiplunker, Hensinger, Kale, and Watch, they gave an algorithm they gave a randomized algorithm in 23, which achieved, again, log k was already there for normal paging. It incurs an extra log square n factor. So we improve it to log n log k. So save this extra log, and we also give it matching lower and upper bound. So essentially, the right bound for min-max paging is log n log k. What about LP norms? Turns out that I won't go through all of this, but essentially we also this also extends to all of those functions where you get a p log k comparative algorithm. So the power p is because in the function g you ignore the 1 by p factor, but you should really ignore this p here. So it becomes p log k. Okay, so if you're looking at LP norm, we get a p log k comparative, and L infinity norm essentially is same as LP norm where p is like log n. So that's why when you put p is equal to log n, you recover this result here. Okay. So this is more general than the previous one. So so we achieved the first results for p bounded paging, and even for LP norm, nothing better was known. People knew such results for the fractional version of those problems, because but nothing was known for the integral version. And again, the approach why people used fractional was because it's easier to deal with fractional algorithms because you can use methods from continuous optimization. You can use gradient descent kind of approaches to these problems. But if you just wanted a integral solution, nothing was known there. And the main contribution is we bypass this step here. Okay, so let me just make it more concrete. What I mean by that. So remember, for weighted paging, you have this template, right? That you're given some input, and as the input is arriving, you're maintaining some fractional solution here. And then on the side, you're maintaining the actual. Actually, this is what you're producing. And this intermediate step is useful because, again, you can use various techniques here. And in weighted paging, you are incurring log k loss here and constant loss here. And you can ask, why can't I do the same thing for max-min paging, right? I mean, why can't I have a fractional solution for max-min paging? I can again write down a linear program there, or some sort of covering program. And again, I can imagine, something like this working out. And indeed, this is what the previous approach did, this paper did. They said that I'll maintain a fractional solution, and in this process, I will lose this much loss in the commutative ratio. And then when I do the rounding, I will lose an additional log n factor here. So if you put these together, you get a log square n log k. And what we observed was, the first thing we observed was that, we showed that both of these bounds are tight. Okay? So if you're going to use this approach, you really can't hope to beat this. Okay? So let me be more precise here. So what we showed is that any fractional algorithm for the max-min problem must incur this much commutative ratio, right? You cannot do better than that. And the integrality gap of that linear program. So the moment you go to the linear program, it has an integrality gap. So the translation from fractional to integral, no matter what you do, will always incur some log factor like this here. So this is, in the weighted paging, one could save this factor because that linear program had integrality gap of a constant, but because it has an integrality gap of log n, this approach cannot give you the optimal bounds here. Okay. And so the main idea that I'll present is that you can actually not go through this two-step process, but run a discretized version of what is called multiplicative update. So multiplicative update is the technique people use for obtaining fractional algorithms. So what I want to show you is that you need not go through this fractional step. You can directly do it in the integral world itself. So this is the main contribution, and so you bypass this gap here. Okay? So even if you have not seen multiplicative update, I'll show you what it is, and I know you can get a feel for it. Okay? So that's what I plan to do in the next 20 minutes. So I want to show you the algorithm for max-min paging, which just uses multiplicative update, but runs a discretized version of this. Okay, and the idea is that, okay, so what I'll just show you the high-level idea here, or high-level assumptions here. So I'll use a black box algorithm for weighted paging. Okay, so I'll assume that if somebody has given me an algorithm which is alpha competitive for weighted paging. Remember what is weighted paging? That every page has a weight, and you want to minimize the weighted eviction cost. Of course, in this problem, there are no weights, right? In max-min paging, there are no weights. So again, let me sort of just make just parse this for you. What this says is that, I'm just restating this assumption here, that if you give me some problem where the optimal value is opt, then this algorithm A incurs weighted eviction cost. So the total eviction cost it incurs is alpha times opt, because alpha is the commutative ratio, plus a small additive factor. And this additive factor is needed because, in the asymptotic sense, when opt becomes very big, this will go away. But we will need this finer level of detail. And this additive term is needed because, for some very basic reasons, right? The starting state of my algorithm and the optimum algorithm may not be same, right? So the starting, the initial stages may not be same. So again, just to do the translation, you may incur some over all of the weights. And again, you can imagine other reasons also. There are other reasons also, because there will always be some initial time where the algorithm will need to figure out what's going on. So even if both of them started with the same state, anything will require some additional additive term just to sort of catch up with the optimum offline. Okay. So all known algorithms will have this structure. Right? I will, in my reduction, crucially use the fact that they are not always at the same initial state. So anyway, point number 1 will apply. So this is what we'll have. Okay. So but whenever you see an alpha competitive, always people mean this, but this may not be written explicitly. Okay. Okay. So this is what it is. What is my goal? Let me restate my goal. My goal is that if you give me an alpha competitive algorithm for weighted paging, I'll show you an alpha log n competitive algorithm for min-max paging. Okay, so this is the reduction I will give. Gamma n is just some sort of function of n. So n square n, right? I'm just assuming something. Assume that I know opt. Okay, so this is an assumption, but again, there are very standard techniques of removing this assumption. And I'll also assume that optimum is, at least some function of n. So let's say at least n square or n cube or something like that. Again, these are very standard assumptions. And the reason why this is standard is because I'm only going in the asymptotic sense where the size of the input becomes much larger than the number of pages or the cache size. So this is anyway, this will get absorbed in the additive term. And we know opt because, again, I can guess opt. There's standard techniques where you guess opt. If it does not work out, you double your guess and so on and so forth. So these are very well known ideas here, that you can always assume that you know the value of the optimum. If not, you will do some doubling kind of argument. And you can also assume that optimum is larger. Right? So both of these are very standard assumptions. Yeah? So I'll assume that. Okay, so let me now go through the algorithm. And you can kind of imagine why weighted paging would be useful, right? Even though I have weights 1 initially, some page, right, my goal is to make sure that nobody gets evicted more than opt number of times. So if somebody is getting evicted too many times, what I'll do is I'll increase its weight, right? That's a natural idea, right? So, so this is what I do. I assign weights to pages, and initially all the weights are 1, right? And the algorithm is going to run in phases. Yeah. Sorry? Yeah, so opt is at least this is some large, I'll specify this. Oh, no, this is opt for max. I'm sorry. No, this is just specifying weighted paging, right? So this is opt for, oh, thanks. Sorry. Yeah. This is the optimum for max min paging, right? I should have used it. Thank you, yeah. This is for max min paging. So we know the optimum value of max min paging, and the optimum for max min paging is at least Bn. So this opt and this opt are different. Thanks. Okay, so the algorithm assigns weights to pages, and initially all weights are 1, and it's going to run in phases. And in each phase, in a particular phase I, I'm going to have some initial weights of the pages. Okay, so let's say in phase I, it should be phase H. In phase H, the weight of a page I is WIH. Okay, and when this phase H ends, it becomes WIH plus 1. Okay, so during this phase, the weight of a page does not change, and yeah, let me just okay. And during the phase, I just run this weighted paging algorithm using these initial weights. Okay, so during this phase, I'll just run my weighted paging algorithm. Okay, so I start with some initial weights of pages. I just run my weighted paging algorithm. When the phase ends, I'll just update the.
Can you go back to the previous one? I'm confused by your previous remark. What was n? N is the length of the.
N is the number of pages. No, not the length. Length is T. T is unbounded. Yeah. So length of the is unbounded. Yeah. So typically in all of these assumptions is that the length of the input is much more than the size of the problem. So yeah. So the yeah. Okay. So again, so right. So there should be phase H. So I'll just I want to run weighted paging. Weighted paging says that you freeze the weights of the pages and just run your weighted paging algorithm. So during a phase, I will not change anybody's weight. So I'll start with some initial weights, just run this algorithm. When phase ends, I'll again sort of update the weights of all the pages. Okay. So you run your algorithm during the phase with whatever the initial weights were. When the phase ends, you just update everybody's weight, and then do this again. Okay, and this keeps on going. And there are just two key issues. When do you say a phase has ended, right? And the thing is, how do you update the weights? And both, as you will see, the algorithm does in a very natural way. It says that you will end a phase when you realize that the weights that I'm using here are no longer consistent with. I mean, these weights are supposed to capture how many times a page has been evicted. So when a lot of action happens in a phase, then you will say that this phase has ended. Let me update the weights. When it is time to update weights, you will end a phase. And how will you update a weight? You will update a weight when a page has been evicted too many times, right? So then you will say that, oh, this is looking like it's getting evicted too many times, so let me make it even more difficult to be evicted. Okay, so that's the complete algorithm. So let me just give you the exact details. The details are, sorry, should have been a phase. A phase ends when if you look at how much cost this weighted paging algorithm incurs, right? That incurs alpha times opt. Opt, remember, is the max min opt, not anything else, right? So you know what opt is, right? So when the total cost incurred by this algorithm, the weighted paging algorithm, when it incurs some alpha times opt, you say that this phase has ended. Let me start a new phase. When do you, how do you update the weight of a page? And this is where the multiplicative update comes in. It says that you're only going to double everyone's weight. So everyone starts with 1 and they'll just keep on doubling. So you double the weight of a page if it has been evicted so many times. So some large constant times this quantity. So 20 alpha opt times since you updated its page last. Okay, so since the last weight update, if you have updated the weight, if you have evicted it at least so many times, then you update the double its weight. Okay, that's it. So this is the complete algorithm. Okay, and I'll show you in 3-4 slides, hopefully, that why it has the required properties. Sorry?
The third point.
This one? Yeah, so you're running a phase, right? What are you doing here? You're running this weighted paging algorithm, right? Because that's the only black box I have. So when this guy incurs too much cost, right? When this guy incurs alpha opt cost, I'll say that let's stop and start a new phase. Because, these weights, whatever they are, they're only some sort of estimates, right? That because the original problem did not have weights. So I need to decide when I'm going to update the weights. Okay. So I can't just keep on, if I run it forever, then maybe the weight of some page was very small, right? Now this is the guy who's getting evicted all the time. So I need to control that, right? So I need to balance two things here.
So you could update the weights at every step, but
Not at every step, only at the end of every phase, at these black points. So think of time as continuous, so lot of requests arrive in between. But when this phase ends, that's the time when you will update it. Because this A cannot deal with changing weights, right? This algorithm A needs a static set of weights. This A cannot deal with changing weights.
phase doesn't necessarily mean that at exactly that point where it's coming, but in between also a phase.
Yeah.
no phase.
Yeah, so the algorithm A is for weighted paging. It says that give me the weights of the pages. I'll run this algorithm. My goal is not to minimize the maximum number of evictions. My goal is to minimize the weighted sum of evictions, right? That's all A does. So A cannot handle change of weights. So for A, it has to be fixed set of weights. And you can imagine a fractional algorithm would be doing this in a continuous sense, but A will always have to be like this. Okay. So as I expected, let me give you most of the, yeah. Sorry. So this opt is the global opt. Global opt, always. So opt forever will mean the global opt of max min. Thanks. Yeah.
A sense when the weighted paging was cut by A, it is alpha times opt, but that
Yeah.
in that case the cost
So this opt here means global opt, right? The one that I have guessed in the beginning.
cost incurred in there.
The weighted cost. Weighted, that's the only thing it can. Yeah. So there are several things going on here, right? Yeah. But here I'm counting. So good. So yeah. When the weighted paging cost, right? Sorry. But you're doubling the page when it has. Here you're counting how many times. Page is getting doubled. Weight is getting doubled when the number of times. Okay. So there's a difference here and difference here. It's subtle, right? Yeah.
So now the
I mean.
to so that the number of phases is small, because each one is, you're losing this alpha.
Sorry.
So each one is alpha competitive. Each phase
A is alpha. In each of these, I'm running an alpha.
and so the number of phases has to be. So will the final competitive ratio be the number of phases times alpha?
No, okay. No, so why? Okay, let me just show the next slide and maybe. Okay, so far so good, right? So let's say T is the last total number of phases, okay? Okay, so how many times do I evict a page? Well, each time I evict it alpha opt times, I double its weight, right? So look at the final weight, right? And take, so the number of times I would have doubled would be log of that. So alpha opt times, because 20 alpha opt times the number of times you doubled it, right? So that's the number of times you evict this page. Okay, opt of course is the optimum value. So this is your commutative ratio, right? Alpha times max. So my goal is to show that this guy never exceeds n. I will show that in fact this is something stronger. I'll show that the total sum of all the weights, when you look at the final end of the last phase, the total weight of all the pages does not exceed 2n. Okay, so once I show this, I'm done, right? Because then this WIT by this result would be also be at most n. So this becomes alpha log n times opt, right? So this is all I have to show. Okay. So let me show you in 2-3 steps why this would be true. So okay, so first of all, I want to claim that the number of phases cannot be too big. Okay, so let me make it too precise. Make it a bit precise. So suppose you consider a phase H. Okay, so suppose there is some phase where the weight of all the pages is bounded. Okay, so suppose I'm at a stage where no page has weight more than 2n. Then I claim that the number of phases till this time cannot be too much, right? So I'll show you why this is true, but it should be intuitive, right? If you spend too many phases, then too many evictions would have happened, and some page would have incurred a lot of evictions, and its weight would have gone up a bit, up a lot, right? So if everybody's weight is bounded by 2n, it cannot happen that the number of phases was very big. Okay, so this is the intuition. I'll show you the proof in a minute, but should be very clear why this is the case, right? So let me just show you a 2-line proof of this. So this will just say that as long as everybody obeys this condition, as long as everybody's weight is at most 2n, the total number of phases will not be too much. Okay, so let's see. Okay, so all right. So let's see why. So well, in each stage, I'm interchanging phase and stage. So in each phase, remember what was the definition of a phase? A phase was ending when the algorithm incurs alpha opt weighted cost. Now the weight of every page is at most 2n, so many evictions would have happened, right? Because nobody is more than 2n weight. So if the weighted eviction cost is alpha opt, number of evictions would have been at least this much. So then some page would have seen at least so many evictions. Okay, over the H phases, right? If the number of phases is H, then some page would have evicted at least this. But no page is evicted more than these many times because the weight of every page is at most 2n. Okay, so that bounds H for you. So if it is too quick, I mean the intuition is that if every page has small weight, too many evictions have not happened. So how can the number of phases be too long? Because you're ending a phase only when a lot of evictions happen. But this is a proof, right? So far so good. Okay.
So how on the previous slide? So when you had for each page it was alpha.
Yeah. So let me do this again.
No, maybe on the previous one. So sorry. So when you're find a competitive ratio. So each page it is alpha opt times log that final weight. But then the actual competitive ratio is alpha times sum of log.
No. So for each page I'm counting how many times it is getting evicted, right?
Yes.
And that's all. I have to take it max over all the pages. Yeah. Okay, so let me just do this again. So in a particular phase, so much weighted cost is incurred, but every page has a small weight. So this translates to number of evictions also. So that's why you're saying that overall the number of evictions will also be large because the weights are bounded right now. Okay, so that's all it is. Okay, so let's say that I wanted to claim that this guy, the total weight never reaches to n, but suppose it reaches to n. Okay, so let's look at the first time when it reaches that quantity. Okay, so you are at a stage where this guy is, let's say, exactly equal to 2n. Okay, now this is the key claim. So there are two claims. This claim says that let's count what is the total cost incurred by A, this algorithm A, right? So remember, A is a weighted paging algorithm. So when I say cost, I mean the weighted eviction cost of A. And let's see how much cost it incurs during this entire H star phases, okay? And I'll put a bound on it, but let's see why this bound comes in, okay? Okay, so how will I do this? Remember, this op is a max-min solution. So now, I mean, if you look at A is running something here, what do I compare it with, right? I know that it is alpha competitive. What do I compare it with? The only thing I can compare it with is the optimal solution for the max-min problem, because that is what I eventually want to connect to. Okay, so let's look at the optimal max-min solution, because that is what I want to connect to. And let's say it incurs some number of evictions in this phase. Okay, so for page I, it incurs those many evictions. Okay, so I know that if you look at a particular phase H, the weighted cost of A, right, this is what it is minimizing, is at most alpha times whatever this actual max-min solution incurs here, which is summation over all I, W, IH, YIH, plus this additive term. And why is that 2n? Because, you know, everybody's weight is at most 2n. Sorry, their weights add up to at most 2n. So this is the cost incurred by A in a phase H. So let's sum it over all the phases. So what will you get? If you sum it over all the phases, this WIH I will bound by the final weight. So this comes out, WIH star, and this becomes summation over, for a page I, summation of YIH, the total number of times this page has been evicted. So this becomes opt here. Okay, and this sum term here. And again, because sum of all the weights is at most 2n, so this becomes 4 alpha n opt. Yeah. So, yeah. So, yeah, so it's just bounding the total eviction cost across all the phases and claim that this is at most 4 alpha n opt. And the reason is that in each phase I'm competitive, so I'm competitive with respect to the actual max-min solution, and that just gives you this. And I want to claim that this cannot happen. Okay. So let's see why this cannot happen. So this is the last slide. So it says that if you look at the pages whose weight is strictly larger than 1. So suppose, you know, this thing has reached 2n. Initially everybody's weight was 1. So if you look at the pages whose weight has increased beyond 1, those guys, their final weight must be at least 10. Why? Because if everybody is going up to 2n, you know, those who did not increase at all, they stayed at 1. So their contribution would have been at most n here. So the guys who increased, their contribution would have been more than n. Okay, and this just gives you a one-line contradiction. Let's see why it is there. So let's look at the total weighted eviction cost of all the pages. Let's look at such a page I. Its weight was it's doubling, right? You're doubling the weights. So look at the time, you know, at some point of time, its weight was half of this quantity. And from there, it doubled to this quantity, right? So from WIH by 2 to WIH, it got doubled. In the intervening period, it must have seen so many evictions. So just for this page, the total number of eviction weighted paging cost would have been WIH by 2 times 20 alpha opt. And if you add this up, it sort of contradicts this quantity. Okay. Yeah, if it looks a bit mysterious, the right setting to do all of this is to look at the dual, right? I mean, you find the dual variables, but essentially the chain of arguments is just using weak duality. But essentially this is the complete proof. Okay. Okay. So this says that this could not have happened, and that's why this algorithm is at most 2n, and it implies alpha log n. Okay. The analysis critically used the fact that that algorithm was a deterministic algorithm. If this algorithm is randomized, this argument breaks down. Then phases become dependent, so I cannot really use Chernoff kind of bounds, but you can use martingale concentration bounds, and turns out everything will work out. So the same algorithm, but you need to do a little bit more. The ideas work for convex paging also. Let me show you why it would work. So remember, you're trying to minimize some function g, and any function g can be written as the integral of its gradient, where y, think of y as this vector y1 up to yn. And now if you look at this integral here, I can discretize it as, you know, over some discrete set of phases, the gradient of g at the beginning of that phase times the length of that phase. So I can always, you know, replace an integral by a discrete summation like this, where ys is just the vector y at the beginning of some phase. And this kind of suggests that, you know, you can run weighted paging where the weight of a page is just the gradient of g, the ith coordinate of the gradient of this g, right? And essentially it says that you will end a phase when this gradient becomes too big. So that's essentially the algorithm. So instead of counting how many times it has been evicted, you use this G, the gradient of this G, to guide how the weights are getting updated. So there are several issues with this. You won't be able to bound the number of phases like the way we did before. The gradient may sometimes grow too fast, so you have to control all of those things. And then randomization, if the algorithm is randomized, you have to do something else, but all of those can be handled. Let me just end with the last slide. So we showed that for online paging, one can do a reduction from weighted paging to max-min paging or to other more general class of objective functions. So can similar techniques be applied for other problems, in particular for K-server, for list update? I'm listing some of them where I think there is hope that such techniques may apply. What about extensions to other class of objective functions? So although this is very general, they don't capture things like top K, right? So you look at the top K most evicted pages and you want to minimize their sum. The number of times those guys are evicted. So max-min says that top one, weighted paging says that you add up everything. And other settings, I mean, this is a very high level question, other settings where discretized version of these multiplicative update outperforms the more well-known continuous version where you follow it by online rounding is this two-step process. Are there other settings where a more direct discretized update would be more useful? Thank you.